Welcome to part 3 of my video playlist about the best methods to convert aliphatic alcohols into alkyl fluorides. This presentation is about the use of difluoroalkylamines as deoxyfluorinating reagents. These are slightly less reactive but more selective than aminosulfur trifluorides and also quite easy to handle. Fluoroalkylamines react with alcohols to yield first alkoxyiminium fluorides, which decompose into alkyl fluorides and amides. Thus, mechanistically, these reagents are similar to the iminium chlorides used for the preparation of alkyl chlorides from alcohols. Neither acids nor bases are required, but due to the formation of hydrogen fluoride, the reaction mixtures should turn slightly acidic. Alpha-fluoroalkylamines are prepared by adding secondary amines to fluorinated olefins. These reactions proceed already at room temperature, and the resulting products show low basicity only due to the strong electron withdrawing effect of the fluoroalkyl group. Specific reagents include the so-called Yarovenko's reagent, discovered 1959, and the closely related Ishikawa reagent. Both can be prepared from inexpensive alkenes by reaction with diethylamine. Newer developments are difluoroimidazolines such as phenofluor, but these are large, expensive molecules and can only be used to prepare expensive target compounds. The main advantages of fluoroalkylamines as deoxyfluorinating reagents are the simplicity of the handling, the mild reaction conditions, the broad scope, and the high yields attainable. Fluoroalkylamines are therefore particularly well suited for expensive, structurally complex starting alcohols. Main disadvantages are the large amounts of waste generated by these reagents and the high price of some of them. In this example, the starting alcohol was a steroid from the 60s, when the development of steroid-based oral contraceptives and anti-inflammatories was in full swing. Despite being a homoallylic secondary alcohol with a high tendency to undergo elimination, mostly the expected fluoride was obtained, together with a small amount of symmetric ether. This type of homoallylic alcohol usually undergoes substitution with retention of configuration because a cyclopropyl methyl cation is formed as intermediate. 2-phenylethyl alcohol also reacted cleanly at room temperature with the addition product of diethylamine to perfluoropropene to give 2-fluoroethylbenzene in high yield, despite the tendency of phenylethyl alcohols to undergo elimination. In the first example on this slide, however, the olefins resulting from beta elimination were formed in larger amounts. Substitutions at secondary hydroxyl groups proceed about 40 times more slowly than primary hydroxyl groups, and elimination can therefore compete more effectively with substitution. Cyclohexanol undergoes elimination particularly readily, and its treatment with difluoroalkylamines did not yield any cyclohexyl fluoride, but only cyclohexene. Particularly difficult starting alcohols are derivatives of serine, as these readily eliminate water to yield acrylates. With the difluoroimidazoline phenofluor, however, a good conversion into the fluoride could be achieved. Unlike the previous examples, the starting alcohol on this slide did not react with difluoroalkylamines at room temperature, but only upon heating. As byproduct, a chloride was formed, but this side reaction could be suppressed by using instead the chlorine-free Ishikawa's reagent. Here is a short summary of the main side reactions. These are eliminations and the rearrangement of carbocations. Then, because of the low nucleophilicity of a fluoride, other nucleophiles, even weak ones, will effectively compete with fluoride. Therefore, with Yarovenko's reagent, alkyl chlorides can be formed as byproducts. Here are some more examples and review articles. The next presentation is about the use of sulfonyl fluorides as deoxyfluorinating reagent. These are still less reactive than difluoroalkylamines and often only applicable to reactive alcohols. See you then.